Good morning, guys. Now, let's see about fifth unit of operating systems. That is the input-output systems. This unit contains input-output hardware, application input-output interface, kernel input-output subsystem, communication with the input-output devices, streams. Now, let's see about one by one. First one, input-output hardware. One of the most important job of an operating system is to manage various input-output devices, including mouse, keyboards, touchpad, disk drives, display, and a display adapter, USB devices, bitmap screen, LED, analog to digital converter, on-off switches, network connection, audio, audio, and input output printers and etc. Category input output devices can be divided into some categories: block devices, character devices. Block devices, a block device is one with which the driver communicates by sending entire blocks of data. For example, hard disk, USB cameras, disk on key, etc. Character devices. A character device is one with which the driver communicates by sending and receiving single characters. For example, serial ports, parallel ports, sound cards, and etc. And device controller. Device drivers are software models that can be plugged into an operating system to handle a particular device. Operating system takes help from a device driver to handle all input-output devices. The device controller works like our interface between a device and a device driver. Input-output units like keyboard, mouse, printer, etc. typically consists of a mechanical component and an electronic component, where electronic component is called the device controller. Any device connected to the computer is connected by a plug and socket, and the socket is connected to a device controller. Uh, a model for connecting the CPU, memory, controllers, and input-output devices, where CPU and the device controller all use a common bus for communications, like memory, monitor, keyboard, USB drive, and a disk drive, CPU, memory controller, video controller, keyboard controller, USB controller, and disk controller. This is the device controllers. Next topic, application input output interface. Input output interface, there is a need of surface whenever any CPU wants to communicate with input output devices. The interface is used to interpret address which is generated by CPU. Thus, surface is used to communicate into input-output device, that is to share information between CPU and input-output devices. Interface is used which is called input-output interface. Various application of input-output interface. Application of input-output is that we can say interface have access to open any file without any kind of information about file. That is, even basic information of file is unknown. It also has feature that it can be used to also add new device to computer system, even it does not cache by any kind of interrupt to operating system. It can also use it to abstract a difference in input-output device by identifying general kinds. The access to each of general kind is through a standardized set of functions, which is called as interface. Next one, character string or block. Character string or block. A character string or block both transfer data in form of bytes. The difference between both of them is that character stream transfer bytes in a linear way, that is one after another, whereas block transfer whole byte in a single unit. Sequential or random access. To transfer data fixed order determined by device, we use sequential device, whereas user to instruct device to seek to any of data storage locations a random access device is used. Synchronous or asynchronous. Data transfer with the predictable response times is performed by synchronous device in coordinates with other aspects of system. And irregular or unpredictable response times not coordinated with other computer events is exhibits by an asynchronous device. Shareable or dedicated. Several processes or threads can be used concurrently by a shareable device, whereas dedicated device cannot. Speed of operations. And the speed of device has a range set which is of a few bytes per second to few gigabytes per second. A read only, write only. Different devices perform different operations. Some support both input and output, but others support only one data transfer directions, either input or output. Next, we will move to kernel input output subsystems. Kernel input output subsystems is responsible to provide many services related to input output. Some of the services provided. What are services? Scheduling, buffering, caching, spooling, and device reservations, error handling. First one, scheduling. Kernel schedules a set of input-output requests to determine a good order in which to execute them. When an application is used a blocking input-output system called, the request is placed on the queue for that device. The kernel input output scheduler rearranges the order of the queue to improve the overall system efficiency and the average response time experienced by the application. Buffering. Kernel input-output subsystem maintains a memory area known as buffer that stores data while they are transferred between two devices or between a device with an application's operation. Buffering is done to cope with a speed mismatch between the producer and the consumer of a data stream to adapt between devices that have different data transfer size. Next one, caching. A kernel maintains cache memory, which is region of fast memory that holds copies of data. Access to the cached copies is more efficient than access to the original. Next one, spooling under device reservations. A spool is buffer that holds output for a device, such as printer that cannot accept interleaved data streams. The spooling system copies the queued spool files to the printer one at a time. In some operating systems, spooling is managed by a stream German process. In other operating system, it is handled by an kernel thread. Next one, error handling. An operating system that uses protected memory can guard against many kinds of hardware and application errors. Next one, communication with the input-output devices. Communication with the input-output devices. The data transfer between the CPU and input-output device may handle in a variety of techniques. Some techniques use the CPU as an intermediate path. Other transfer the data directly to and from the memory unit. The data transfer to and from peripherals that are sharing input-output communications. The types of input-output communication technique: programmed input-output, interrupted initiated output, input-output, direct memory access. First one, programmed input-output. In the program input output method, the input output device does not have direct memory access. The data transfer from an input output device to memory requires the execution of a program or several instructions by CPU, so that this method says programmed input output. In this method, the CPU stays in a program loop until the input-output unit indicates that it's ready for data transfers. It is a time-consuming process for the CPU. The programmed input-output method is particularly useful in small, low-speed computers. The CPU sends the read command to the input-output device and wait in the program loop until it receives a response from the input output devices. Next one, interrupted initiated input output. The problem in programmed input output is that the CPU has to wait for the ready signal from the input output device. The alternative method for this problem is interrupt initiated input output or interrupt driven input output. Interrupt incident input output method, the CPU issue a read command to the input output device about the status and then go on to do some useful work. When the input output device is ready, the input output device sends an interrupt signal to the processor. Next, direct memory access. Direct memory access is a process where the data transfers between the microprocessor or CPU, the memory and peripheral device directly without the involvement of the microprocessor. The CPU first initializes it and the CPU should send some useful information to the DMA controller. Is the diagram shows the operation of DMA transfers. The CPU is DMA controller to block address, word count, and control. This is a control of the DMA controller. Next, disk controller. This DMA request is moved to the disk controller. The disk controller is again the assignment to go to the DMA controller from disk controller. Then the drive buffers and main memory data transfer to from disk controller to main memory. This through bus. Letting the DMA controller is to manage the memory buses directly. It would improve the speed of transfer. A chip says a DMA controller manages this process. The CPU is idle and it has no controller of the memory buses. A DMA controller takes over the buses to manage the transfer directly between the input-output device and memory. Next one, streams. I have full duplex communication channels between user and the level process and their device in Unix system 5 and beyond. A stream consists of stream head interface, driver, and interface with the device, zero or more stream module between them. Each module contains read queue and write queue. Message passing is used to communicate between queues. This diagram shows how to data flow in streams. User process the data flow to stream head, read queue, and read queue, and etc. And driver end, and then we'll move to and device, then it revert back this process. This is the stream output for the data. Thank you.